So this is about the methods for determining the velocity of a point on a link, right? So we studied about the links and joins and pairs, right, and number of links and all. Now we are going to study how can we determine the velocity of a particular point on a link, right? So we can determine the velocity by two methods. One will called as instantaneous center method, and the other one is relative velocity method, right? Instantaneous center method and relative velocity method. So we'll see how can we find the velocity by the instantaneous center method. All right. Velocity of a point on a link by instantaneous center method. We'll assume this as a body, right? This as a body. Okay. And here at this point A on this body, we have the velocity VA this side. And this is the point B. And here we have the velocity this side, VB, right? We'll assume. So this is the body. Point A is here. The velocity is acting on the body in this side, VA. And this is the point B. And velocity is acting on this way, which is called as VB, right? So we can use this method to find the velocity of any links, like four-bar mechanism, quick return mechanism, right? Slider crank mechanism. So we can find the velocity of any points on those links. So we'll use this method, right? We'll see how to find that, right? Consider 2 points A and B on a rigid link, right? So this is the rigid link, okay? And these are 2 points A and B. Let VA and VB the velocity of points A and B, whose directions are given by angles alpha and beta as shown in the figure, right? So this is VA, which is making an angle alpha with AB, and this is B point. Here is the VB, velocity B, which is making an angle beta with this AB line, right? If VA is known in magnitude and direction, right? If VA is known in magnitude and direction, right? So we know velocity is a vector which can be denoted by the magnitude and direction, right? So the length of this arrow is denoting the magnitude and the angle is denoting the angle where it is acting, right? Similar way, this VB, the length of this arrow is the magnitude of the velocity, and the direction which is making is the direction where the force is acting, right? So if VA is known in magnitude and direction, and VB in direction only, and VB in direction only, so we don't know the velocity magnitude, then the magnitude of VB may be determined by the instantaneous center method, right? So if I know the magnitude and direction of one velocity, I can determine the magnitude and direction of the other velocity by the instantaneous center method, right? Here we'll see now resolving the velocities along AB, right? So here we'll see this is AB, right? This is AB. So now what we are going to do is resolving the velocities along AB. So we know a velocity can be determined resolved in two directions, right? Perpendicular to and parallel, I mean along with, right? So if this is VA, I can write this as VA cos alpha, right? Why this angle is alpha? This is VA, so I can write this as VA cos alpha. All right. Similarly, you know, we can write, if I resolve it in this direction, okay, if I resolve it in this direction, I can write it as VA sin alpha, okay. So here, for this example, we don't need this, I'm just saying. So if this is VA, we can resolve it along with alpha as VA cos alpha and opposite to alpha as VA sin alpha, right? So now what we are doing is we are resolving this vector along this line AB, right? Along this line AB. So this is VA cos alpha, right? Along the line A, which is equal to VB cos beta. So here what we have is VB, right? So this can be resolved along with AB line as BB cos beta, right? So with the angle that is BB cos beta, right? If it is perpendicular to the angle, which can be denoted in this way as BB sin beta, right? BB sin beta. So sin I am writing as S, okay? And this we can write it as BA sin alpha, okay? We can resolve the force or vector or velocity in two direction. One is along the axis what we are taking, and the other one is perpendicular to the axis, right? This is general. So now what we are going to resolve is only with the axis AB, right? We don't need the sin beta for now, okay? So resolving velocities along AB, this is AB, that is VA cos alpha along the angle, that is cos alpha, and BB cos beta, right? So now along the axis AB, right, VA cos alpha and BB cos beta are same, right? So now I can solve it, okay? I will bring this VA upon BB, right? So VA upon BB equal to cos beta upon cos alpha, right? Cos beta upon cos alpha. So VA upon BB is equal to cos beta upon cos alpha. And you know, cos beta can be written as sin 90 minus beta, right? Similar way, cos alpha can be written as sin 90 minus alpha. So if I take a triangle, okay, and if this angle is alpha, okay, I'll write it as A, B, and C, all right? So if this is alpha, you know this is 90, right? I'm saying a right angle triangle. So if this is 90 and this is alpha, this is 90 minus alpha, okay? This is 90 minus alpha. Why? You know, a triangle, the total of internal angle is 180, right? So if you add this, and this, that will give you 180. How? This is 90 minus alpha plus this is alpha. So this minus alpha and this plus alpha will be gone. So 90 plus this angle, that is another 90. So 90 plus 90, 180, right? So based on this, I can write this angle as 90 minus alpha. So if I am going to write sin alpha, okay, if I am going to write sin alpha, I can write it as opposite over adjacent, right? So opposite is BC, right? Opposite to alpha, that is BC, upon adjacent, that is AB, not adjacent, sorry, hypotenuse, okay, that is AB. Okay, so sin alpha can be written as opposite upon hypotenuse. Similar way, cos alpha can be written as adjacent, right, that is AC, upon hypotenuse, right, that is AB. Right, so this is opposite and this is adjacent, right, and this is hypotenuse. AB is hypotenuse. This is how we call it, okay? So this is hypotenuse. For this particular angle I am talking, this alpha, this is hypotenuse, this is opposite, and this is adjacent sides, okay? So cos beta, okay, cos alpha, we'll talk about cos alpha. So cos alpha here is AC upon AB, right? AC upon AB. So this cos alpha is equal to this sin 90 minus alpha. Why? Sin 90 minus alpha, that is opposite over hypotenuse, right? So sin 90 minus alpha is opposite upon hypotenuse. So for this angle, right, I'm talking about this angle. You see sin 90 minus alpha. So I'm talking about this angle. For this angle, the opposite is this one, right? Opposite is this one, that is AC upon hypotenuse. Hypotenuse will never change, right? Always the side opposite to the right angle is the hypotenuse, right? Side opposite to the right angle is the hypotenuse. So this is not going to change. So that is AB. Okay. So there you see cos alpha is equal to AC upon AB. Sin 90 minus alpha is also AC upon AB. So this AC upon AB and this AC upon AB is equal, right? So cos alpha and sin 90 minus alpha are equal, right? This is a general rule. So I can write cos alpha as sin 90 minus alpha anytime, anywhere, right? Not only for this case, I can write anytime, anywhere cos alpha as sin 90 minus alpha. Similar way, I can write cos beta also sin 90 minus beta, right? So if I write instead of alpha, I here write beta here. So this will change as beta, this will change as beta, and this will change as beta. So again, we will have same results, right? So cos beta is equal to sin 90 minus beta. Okay, so we'll hold this as equation number 1, right? Then we will apply Lami's theorem to triangle ABA, right? So there's a triangle, theorem called Lami's theorem, right? So I'll tell you what is that. Now we are going to see the angle ABI, right? Triangle ABI. Okay, this is our triangle. AI upon sin 90 minus beta. Okay, AI. Okay, this side upon sin 90 minus beta. Okay, this angle is the sin 90 minus beta. Why? This is beta. Okay, therefore this is 90 minus beta. Why? This is right angle. Okay, and if this is 90 minus beta, sorry, 90 minus beta, then this is beta. Why? This is right angle. Okay, so if this is 90 minus beta and this is beta, then this is 90 minus beta. Okay, so I can make this diagram more clear. Okay, so this is the line VB cos beta. This is going like this. Okay, and here is the VB. All right, this is VB and this is VB cos beta. So for my easiness, I'll write cos beta as C beta and the sin beta as S beta. Okay, and this angle is given as beta. All right, and there's a perpendicular. Okay, this is a perpendicular. So perpendicular means this whole angle is 90 degree, right? So if this whole angle is 90 degree and this is beta, this can be written as 90 minus beta, right? Why? When you add this 90 minus beta and beta, you should get 90 degree, right? So this angle is 90 minus beta. And then I have a line here, right, which is perpendicular to this line. Okay, this VB, this I is perpendicular, and here I have the AB. So this will be going like this. Okay, so if this is a perpendicular, right, this whole angle is 90, right? So VB, I put this as O, right? If VBOI is a perpendicular, sorry, not perpendicular, right angle, and if 90 minus beta is there, that is VBOI, right? VBOI is 90 minus beta, and VBO, okay, I will put some other letter for this. I will put it as J, okay? It's already there. So I put it as J, okay? VBOJ is 90 minus beta and VBOI is 90, then this angle will be coming as beta. All right. And now this JOA, this is another right angle, right? JOA, this is another right angle. So if JOA is a right angle, and if this is beta, and this will be again 90 minus beta. Why? When you add this 90 minus beta and beta, you should have 90 degree, right? So JOA beta plus 90 minus beta. So this plus beta and this minus beta will be cancelled out and we will have 90. Okay. So this is why this angle is 90 minus beta. All right. So what your Lamis theorem saying is AI upon sine of the angle opposite to that side, right? A triangle will have three sides. Okay. A side upon the sine of angle opposite to that side, the ratio will be equal, right? So AI upon sine of this angle, that is ABI, will be equal to BI upon sine of the angle opposite to that, right? So that is BAI, right? Sine of the angle opposite to that will be equal to AB upon sine of the angle opposite to that, right? That is AIB. So this is our Lamis theorem, right? So now I will write it as AI upon sine 90 minus beta, sine of the angle opposite to that, right? So this angle is 90 minus beta. I have proved here, right? So AI upon sine of 90 minus beta will be equal to BI, right? Here's our BI. This BI upon sine of the angle opposite to that, that is sine 90 minus alpha, right? So you can check this also in similar way, right? If this is alpha and this is 90 degree, then this will be 90 minus alpha, right? So AI upon sine 90 minus beta will be equal to BI upon sine 90 minus alpha will be equal to AB upon sine of this angle, but we don't need them. Why? Because I don't need that component here. I need sine 90 minus beta, sine 90 minus alpha, but I don't need this component, so I'm not writing it. Okay. So now we'll solve it again. AI upon BI, okay, AI upon BI is equal to sine 90 minus beta upon sine 90 minus alpha, right? Sine 90 minus beta upon sine 90 minus alpha, okay, that we will consider as equation 2. All right, already we have an equation that is 1 sine 90 minus beta upon sine 90 minus alpha, that is equal to VA upon VB, which is equal to cos beta upon cos alpha. This we have already here. And now we derived another equation, A upon BI, which is equal to sine 90 minus beta upon sine 90 minus alpha, right? So from this equation 1 and this equation 2, this sine 90 minus beta upon sine 90 minus alpha is equal to VA upon VB, and it is equal to AI upon BI. All right. So after this derivation, I can write VA upon VB is equal to AI upon BI, which will be equal to sine 90 minus beta upon sine 90 minus alpha, right? Why? Both the sine 90 minus alpha, beta upon sine 90 minus alpha. So sine 90 minus beta upon sine 90 minus alpha is equal to VA upon VB is equal to AI upon BI. Okay. Oh, VA upon AI. So now we are bringing this AI here and VB there. So VA upon AI is equal to VB upon BI, right? VA upon AI is equal to VB upon BI. So VA is a velocity, right? V is a velocity, VA is a velocity. AI is a distance, right? AI is a distance. So VA upon AI, velocity upon distance. Okay. So you know velocity upon distance will give you the angular velocity. Okay. Omega. Okay. VA upon AI is equal to VB upon BI is equal to omega. Okay. So if the velocities are, even if the velocities are varying in different points on a link, the omega, that is the angular velocity, is the same, right? So that's the conclusion. Even if the velocities of a rigid link are different in different points on the link, but the angular velocity is same. Because you see here, this is the point A and the velocity is VA, that is different velocity. Here, this is point B and this is VB and this is different velocity and different point. And randomly, I am taking another point C here. Okay. So the point's velocity is VC and the point is C, and that is another different velocity and different point. Okay. But after the end, we will have same angular velocity. All right. So VA upon AI will be equal to VB upon BI, which will be equal to omega, right? So if a rigid body is in a motion, then we can apply this one. If C is another point on the link, then, right, if C is another point on the link, so here is a C, okay? So we can write VC upon CI will also be same. This is a general conclusion. So VA upon AI will be equal to VB upon BI, will be equal to VC upon CI. If I am taking another point D somewhere here, which will be equal to VD upon DI. All right. So this is a general conclusion. Okay. So now we'll see what are the general conclusions we can get from this above equation, right? If VA is known in magnitude and direction, okay. If VA is known in magnitude and direction, and VB in direction only, and VB in direction only, so we don't know the magnitude. Then velocity of point B or any other point C, right? Any other point C. C does not need to be here. It can be here, 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 anywhere. Lying on the same link may be determined in the magnitude and direction. So for that, we need a point that points velocity and magnitude, right? So direction and magnitude of the velocity, and any other point only with the direction, right? Then we can determine the velocity of that particular point. The next conclusion, the magnitude of velocities of the points on a rigid link is inversely proportional to the distances from the points to the instantaneous center and is perpendicular to the joining the point to the instantaneous center. Okay. So which means, so here AB, okay, this is a link. VA is the velocity. So the direction perpendicular to VA is this direction. Okay. Similar way, this dotted line. Here is our velocity VB. Okay. So this is the link, and this is a line joining the velocity with. Okay. And perpendicular to that, that is this direction. Okay, this dotted line. So this dotted line and this dotted line, they meet at a point, and this particular point is called as the instantaneous center, right? This is the I, right? That's why we call it as I instantaneous center. So the magnitude of velocities of the points, this is a magnitude on a rigid link, is inversely proportional to the distances, right? So if the distance increases, the magnitude will be decreasing. Distances from the points, right? From the points to the instantaneous center and is perpendicular to the line joining the point to the instantaneous center, right? So this distance, if it is increasing, the velocity would be decreasing. That's why it's mentioned as inversely proportional to. All right. And this is perpendicular to the velocity. Okay. This is perpendicular to the velocity. So these are two conclusions we can derive from the above equation. So velocity, if it is acting on a direction, the instantaneous center would be always perpendicular to that, right? And if the distance between the velocity acting point and the instantaneous center is increasing, then the velocity would be decreasing, right? These are the two conclusions. Then we'll go to the types of instantaneous centers, right? There are three types of instantaneous centers. Okay. One is fixed instantaneous center, right? Other one is permanent instantaneous center, and then third one is neither fixed nor permanent instantaneous centers, right? And these two combinedly we call them as primary instantaneous centers. Fixed and permanent we call them as primary instantaneous centers. And this third one, neither fixed nor permanent, we call it as secondary instantaneous center, right? So first two type, that is fixed and permanent, we call it as primary. And the third type, it is secondary instantaneous center. All right. So now we'll see how to locate those instantaneous centers. Right. So now we'll go for a 4-bar mechanism. Right. So you know this is a 4-bar mechanism, and we have 4 links, 4 joints. Right. We'll mark the instantaneous centers here. Right. So here you see link 1, link 2, link 3, and link 4. Right. These are 4 links. The point joining the link 1 and link 2, there will be an instantaneous center which is called it as I12, right? The point is joining the link 1 and the link 2, that's why it is called as I12. This is read as I12, not as I12, right? Don't read it as I12, I23. This is written and read it as I12. Similar way, this link 2 and link 3, the instantaneous center joining these two will be known as I23. Okay. And link 3 and link 4 is called as I34. And this one, which is joining the link 1 and link 4, that is link 1, 4. Right. Among these 4 links, right, I14, I12, I23, I34, this I14 and this I12 are known as fixed instantaneous center, right? Fixed instantaneous center, because this link is a fixed link. You see here this mark. So this mark is used to denote the fixed link, right? So this is a fixed point. This is a fixed point. Therefore, this is a fixed link. So the instantaneous centers located on that link, we call them as fixed instantaneous center, right? So I14 and I12, these are fixed instantaneous centers. Then we have 2 more, I23 and I34. So these 2 instantaneous centers are known as permanent instantaneous centers, right? These 2 are known as permanent instantaneous centers. Combinedly, this I12, I23, I34, and I14, combinedly these 4 are called as primary instantaneous centers. All right, primary instantaneous centers. And here we have one I3, and there I have one I24, right? These 2 are called as neither permanent nor fixed instantaneous center. So these are the secondary instantaneous centers. I13 and I24, these are the secondary instantaneous centers. So we'll see how to locate them. So these 4 you can locate easily, right? So the joints joining them, that point would be the instantaneous center. And these 2, right? These 2, we need to project these all 4 links, right? So projection means, you know, we can project this line like this, right? And we can project this line also. Okay. I will project this line also. Okay, yeah, that's going somewhere else. And I will project this line also. So once you project every line, you will see the entire lines will meet only at another 2 points. Okay, if it is going this way and if it is going this way, this is not going to meet anywhere, right? Similar way, if this is going this way and this is going this way, this is not going to meet anywhere, right? So once you project those lines, they will meet at another 2 points, and those 2 points are the other 2 instantaneous centers, right? And these are called as secondary instantaneous center, right? Right. Now we'll see how to locate them. Okay, locating the secondary instantaneous centers. So this is a link which you have seen in the previous diagram, 4-bar mechanism. Okay. So in order to join, in order to locate these 2, right, but what we have to do is we need to just draw a circle, right? Just a circle. And then you need to mark these 4 links, 1, 2, 3, and 4, right? So we will mark it as 1, 2, 3, and 4. Okay. Then you have to join them. All right. So in order to find the other 2 instantaneous centers, already you have found 4. In order to find these 2, okay, what we have to do is join 2 such points that the line joining them forms 2 adjacent triangles in the circle diagram, right? So now I mark these 4 points, 1, 2, 3, 4, right? I mark these 1, 2, 3, 4. I joined them. Okay, I joined them. Then I can put the link name also, right? So this is link 1, link 2, link 3, and link 4. So instantaneous in the 1, 2, 3, and 4. So this part is over. Now, in order to make these 2 points, I have to join this point and join these 2 points. Okay, by the cross dot line, right? Because these are the only possible way I can join this, right? If you take the point 1, 1 is joined with 2, 1 is joined with 4, 1 is not joined with 3, so I can make only that line, right? So no problem with that. Similar way, I will mark for 2 also. So 2, I can join only with this, right? So then I put these 2 dotted marks. So in order to make this, I need to look for the 2 adjacent triangles, right? Adjacent triangle means 1, 2, 3, okay? 1, 2, 3, and 1, 4, 3. These are called as adjacent triangles, okay? Adjacent triangles. Similar way, 1, 2, 4, okay? And 2, 4, 3 or 2, 3, 4. These are called as adjacent triangles, right? So this complete diagram need to form 2 adjacent triangles. Adjacent triangle means 2 triangles where a common side should be shared with. Okay. So if I take this 1, 2, 3, not 1, 2, 3, 1, 2, 4 as one triangle, and this 2, 3, 4 as another triangle. Okay. These 2 triangles are sharing a common line here. Okay. So these can be considered as adjacent triangle. Which 2? 1, 2, 4 and 2, 3, 4. They can be considered as adjacent triangles. Okay. Similar way, I'll draw another diagram, then that would be easy. Now I will draw a triangle 1, 3, 4. Okay. 1, 3, 4. This is a triangle. Similar way, I will draw another triangle 1, 2, 3 also. Okay. So if you see this 1, 2, 3 and 1, 3, 4, they are sharing a common side, right? So these 2 are called as the adjacent triangles. Okay. But you can't say this is an adjacent triangle if it is not sharing a common line. Okay. So I will write it as 1, 2, 3, 4. Okay. I will draw a line like 1, 3, 4. Okay. This is a triangle. And I can draw 2, 4, 3. Okay. I will draw 2, 4, 3. If you see these 2 triangles, there is no adjacent triangle, and we can't say because there is no any cross joint is sharing with it, right? So don't assume this as sharing, right? This is not sharing the side, adjacent side, right? So this should not be intersecting with this. So if you consider this region is common for both the triangle. This is not adjacent triangle, right? If you see here, only the side is being shared and there is no intersection between these 2 triangles, right? Similar way, there is no intersection between these 2 triangles. So these are called as the adjacent triangles. This is not the adjacent triangle. All right. Okay, so we'll be back. The line which is responsible for completing 2 triangles, right? The line which is responsible for completing these 2 triangles. So if this line is not there, then this triangle is not complete, right? completing two triangles should be a common side to the two triangles, right? It should be the common side for these two triangles. In this figure, join 1 and 3 to form the triangles 1, 2, 3 and 3, 4, 1, right? 1, 2, 3 and 3, 4, 1. Okay, we are talking about this diagram now. So 1, 2, 3 and 3, 4, 1. And the instantaneous center L13, right? So L13 is here. Okay, not L. Okay, I put it as I, instantaneous center. No? So that is I13 will lie on the intersection of I12, right? So this is the I12, I23, okay, and I14, I34, I34, I14. Right? The intersection of these two produced if necessary on the mechanism. So I need to produce it, right? Otherwise, it will not meet. So I23, I21, this link, and I14, I34, that is this link. If I produce these two, they will meet at a point. Okay, on the mechanism. Thus, the instantaneous center I13 is located, right? So this is how we locate the instantaneous center I13. Join 1 and 3 by a dotted line, right? Join 1 and 3 by a dotted line on the circle diagram and mark number 5 on it, right? And then mark a number 5 on it. So this would be the next instantaneous center. So here we have 1, 2, 3, 4. That's already there. 1, 2, 3, 4. Now, once you produce this one, we will have the next instantaneous center 5, right? Next instantaneous center 5. So 1, 2, 3 and 3, 4, 1. These are the two triangles, right? 1, 2, 3 and 3, 4, 1. 3, 4, 1. These are the two triangles. So that's why we are considering I12, 2, 3, right? I12, I23 and I14, I34, right? I14, that's here, I34, right? Here I12 and I23. Okay. Now we have found the fifth instantaneous center. Similar thing we are going to do for the next instantaneous center also. All right. So what we can do is similarly the instantaneous center I24, which is I24. I will mark it with another color. Right, I24 will lie on the intersection of I12, I14, right? So now we are going to talk about, so this triangle problem is over. Now we are going to discuss about this triangle, okay? So thus intersection of I12, I14, right? I12, I14. So I12 is here. Okay, I14 is here. I am going to produce this line, okay? And I23, I34, right? I23, I34. I am going to produce this line also, okay? And they are going to meet at a point. Produce if necessary. Anyhow, it is going to be necessary on the mechanism. Thus, I24 is located. So here I located the I24 at the intersection of these 2 points. Join 2 and 4 by dotted line, right? So now join this 2 and 4 with a dotted line on the circle diagram and mark 6 on it, right? So that is 2 and 4 is joined and marks 6 on it. Hence, all the 6 instantaneous centers are located, right? So totally, we must have 6 instantaneous centers. I will say why. There's an equation to find them. Okay. So there must be 6 instantaneous centers, and we have located it. 1, 2, 3, 4, 5, and 6. Right? Altogether, 6 instantaneous centers, and we have located it. Okay. So now we'll see why there are 6 instantaneous centers. So there's an equation. Okay. The instantaneous centers I12 and I14 are called as fixed instantaneous centers. Okay, so I told you if the instantaneous center in the fixed link, we call them as fixed instantaneous centers, right? So a fixed link is a link which is grounded, right? That is grounded. This is called as a fixed link, right? Which is grounded. We call it as the fixed link. All right. So here this is a fixed link. So I14 and I12, I14 and I12 are called as fixed instantaneous centers since they are in the fixed link. Okay. As they remain in the same place for all configuration of the mechanism. Why? Because when this mechanism moves, right, if you consider this as a crank and this as a rocker, so once it makes a complete rotation, that may move here and in this way, right? Whatever the motion it makes, this link is not going to make any movement. Okay, so that's why this and this are called as fixed instantaneous centers, as they remain in the same place for all configuration of the mechanism. The instantaneous centers I23 and I34, right? I23 and I34. I23 is here and I34 is there. Are the permanent instantaneous centers. Right? These are the permanent instantaneous centers as they move when the mechanism moves. Okay, so when this mechanism moves, this may move, right? So now it is in this configuration, this is like this. Maybe if it make a movement like this, okay, this I34 will come here and I23 will go there, right? So when this mechanism makes any movement, these links will also move, but this will not move. Okay, so as they move when the mechanism moves, but the joints are permanent nature. Okay, so here you see this joint and this joint, these are permanent. So whenever it makes any movement, there's nothing going to happen for these two joints, right? So since these are permanent nature, we call it as permanent instantaneous center, right? So the instantaneous centers associated with the permanent links, we call them as permanent instantaneous centers, as they move when the mechanism moves. But the joints are permanent nature. Then the instantaneous centers I13 and I24, right? I13 and I24 are neither fixed nor permanent instantaneous centers, right? So they are neither fixed nor permanent. They are not even fixed, right? There's no any fixed link, and they are not permanent. Why? They are not associated with the permanent joints, as they vary with configuration of the mechanism. Okay, so they don't have any fixed part. Okay, these two don't have any fixed part, and they are not associated with the permanent links or joints, so they don't have any permanent nature. That's why it is called as neither fixed nor permanent instantaneous center. Okay, the instantaneous center of two links such as link 1 and link 2 is usually denoted by I212. I told you, right? So link between link 1 and link 2 is noted as I12, and it is read as I12 and not as I12. Okay, so don't read it as I12, and it is called as I12. And there's a formula to find the number of instantaneous centers. Okay, the number of instantaneous center capital N is equal to n into n minus 1 by 2. Okay, so this small n is the number of links. Okay, and this capital N is the number of instantaneous centers. So number of instantaneous centers on a mechanism is equal to the number of links n into n minus 1. That is number of links minus 1, n into n minus 1 by 2. That is 4. So this is a 4 bar link, right? 1, 2, 3, 4. 4 into 4 minus 1, n minus 1, 4 minus 1. How much is 4 minus 1 is 3. 4 into 3 is 12. 12 by 2 is 6, right? So in a 4-man mechanism, you should have 6 instantaneous centers. So if you calculate here, 1, 2, 3, 4, 5, 6. Okay, there will be 6 instantaneous centers. Right, location of instantaneous centers. All right. So when the two links are connected by a pin joint or pivot joint, the instantaneous center lies on the center of the pin as shown, right? So here we have two links. This is link 1 and this is link 2. Right? This link and this link are connected by a pin joint. Right? They are connected by a pin joint. And this link instantaneous center is known as I12. You know, right? Link 1, link 2. The instantaneous center is measured as I12. Okay? Instantaneous center between link 1 and link 2. Such an instantaneous center is of permanent nature. Right? So if this link and this link, if these two can move, this instantaneous center is going to be the permanent instantaneous center. Right? But if one of the link is fixed, right, either one of this or this is fixed, then the instantaneous center will be of fixed type. Right? So since one joint is fixed, right, we know if either one of the joint is fixed, then this instantaneous center is going to be fixed instantaneous center, because only one link can move, the other one is fixed. Right? So there we will mention this instantaneous center as fixed instantaneous center. But if this link and this link, if these two can move, then we call it as permanent instantaneous center. Right? So if these two can move, then there is permanent instantaneous center. If either one of this is fixed, then it is of fixed instantaneous center. All right. Then we will go to the next type. When the two links have a pure rolling contact, right? This link, link 2, is rolling on link 1, right? So this is how it is going to roll, right? You know what is rolling is. When the two links have a pure rolling contact, so there is no slip, right? There is no slip. This should roll, okay? It should not slip. That is, link 2 rolls without slipping upon the fixed link 1, which may be straight or curved. So this fixed link, you see this diagram, this is fixed link. So this fixed link can either be a straight link or a kind of curved link, doesn't matter. Only thing is this one should exhibit a rolling contact, right? So this should exhibit a rolling contact. This should not slip. So that's that. Then the instantaneous center lies on the point of contact, right? So if one body is rolling on a fixed link, then the instantaneous center is at the contact point of these two, right? So this roller and this straight fixed link are connected at this particular point, right? So at this contact, the velocity of any point A on the link 2 relative to the fixed link 1 will be perpendicular to I12A and is proportional to I12A, right? So we will take any arbitrary point A, right, on the roller, that is link 2. Alright. So the line joining the instantaneous center and the point A, right, the row line, the velocity will be perpendicular to that line, right? So the velocity will be perpendicular to the line which is joining the instantaneous center and the particular point. Okay. So if I take any arbitrary point B, we'll draw a line from instantaneous center to the line, that is I12B. The velocity will be perpendicular to that link, right? 90 degrees, so perpendicular to that link. So when this is moving this way, right, velocity is going to be on this direction, right? So velocity of any point A, so it can be somewhere here A, another point B, somewhere here C, right? Any point on the link 2, right? This is link 2 relative to the fixed link 1, right? So relative to the fixed link 1 will be perpendicular to the line I12A, right? I12A perpendicular to that, and is proportional to I12A, right? So if this distance is high, then velocity would be high. If this distance is low, then velocity would be low, right? That's why it's mentioned as proportional to I12A, right? Proportional to this distance. So VA upon VB, VA is the velocity of point A and VB is the velocity of point B, right? So VA upon VB is equal to I12A upon I12B, right? This distance upon this distance, the ratio will be VA upon VB, which means if the distance between I12 and this point is increasing, the velocity will also be increasing. If the distance between this I12, the instantaneous center, and B, if it is decreasing, then the velocity will also be decreasing, right? Then we have the third type, when the two links have a sliding contact, right? So slide diagram mechanism is an example for us. Okay, this is a fixed link, and there's another link which is sliding on this. There's no any other movement. It is sliding on this. So when the two links have a sliding contact, the instantaneous center lies on the common normal at the point of contact, right? So common normal, that is the normal drawn between this link 1 and link 2, right? That will meet at infinity, right? So if I have a point A here, another point B here, right? This is the fixed link, link 1, right? This is the fixed link. And this slider is the link 2 which can move on this link 1, right? The instantaneous center between this link 1 and link 2 will be normal to this and will meet at infinity, right? So I12 at infinity. So when the link 2 slider, right? Link 2 is the slider, moves on fixed link 1, right? Moves on fixed link 1, having straight surface as shown in this figure. Okay, this is straight surface. The instantaneous center lies at infinity, right? Instantaneous center lies at infinity, and each point on the slider has the same velocity. So here, whatever the point you take in this slider, A, B, somewhere here, C, somewhere here, D, E, any point will have the same velocity, right? So for slider, the velocity of any point on the slider will be equal, right? So this is another type of instantaneous center. So then what will happen if we have a curve link, right? So this is also slider, but here the fixed link is a kind of curve, right? The previous one, that's a straight line. So here again, link 2 is the slider and link 1 is the fixed link, right? When the link 2 slider moves on fixed link 1, right? Slider, that is link 2, moves on link 1, that is fixed link, having curved surface as shown in this figure, right? The fixed link is curved. The instantaneous center lies on the center of curvature of the curvilinear path, right? In the configuration at the instant. So center of curvature means about which point this curve is drawn, right? About which point this curve is drawn is what called as the center of curvature of the curvilinear path, right? So if you take, this would be probably normal to this contact region, right? So I'll draw. So if I extend this point, I mean this line somewhere here, okay, this contact is normal. Normal means 90 degree. Okay. Similar way, if I extend the A also, I can extend like this, right? So this point of contact would be normal. Alright, this is 90 degree, right? So this is how we determine. So here the curvilinear path is shown, the slider is moving, right? The point of contact is here, the line drawn normal to this contact. Similar way, the line drawn normal to this contact will meet at a point, right? And this point is going to be the instantaneous center, right? That is I1, 2. 1, 2 mean 1 is the fixed link, 2 is the slider, I is instantaneous center, so we call it as I1, 2, right? So the instantaneous lies on the center of curvature of the curvilinear path, right? So about which point this curvilinear path is made, on that point the instantaneous center will lie on, right? When you do the numericals, you need to consider these things, whether the motion is a pin joint motion, pivot joint motion, or slider crank motion. Then only you can note the instantaneous center. If it is a slider crank in the straight line, then that will meet at an infinity, right? And if it is a curvature, then that will meet at the center of curvature of the curvilinear path. So you need to see while doing a numerical about these instantaneous centers. All right. Then we will go to the last type. When the link 2 slider moves on a fixed link 1 having constant radius of curvature. So the difference between previous case and this case is here the radius is fixed and this is a kind of circle, right? The previous case, that's a kind of curvilinear path, so that's not a complete circle, that's just a curve. Okay, so that curve does not represent a complete circle. That may not be a complete circle, but here that's a complete circle. Okay, so which means the radius is constant. When the link 2 slider, this one is a slider, moves on link 1, this is a fixed link, right? When you see this type of lines, you need to understand this is a fixed link. Fixed link 1 having constant radius, right? This radius is constant. The instantaneous center lies at the center of curvature, right? Center of curvature, right? That's the center of the circle for all configuration of the links. So this is a special case. If the slider is somewhere here, or somewhere here, or somewhere here, or somewhere here, the center is going to be the same, right? Since this is a circle and the radius is constant, right? So in this case, the instantaneous center will lie at the center of the circle, right? Center of the curvature. Previous case we mentioned as center of the curvilinear path, since that is not a complete circle. But here this is a complete circle. So if I take any arbitrary points like A and B, okay, so A join it with instantaneous center, the velocity would be perpendicular to that VA, right? Similar way to B, here we have the B, right? Join it with instantaneous center, velocity is perpendicular to that, right? So here the instantaneous center will always lies at the center of the circle. Right? So these are the instantaneous centers and types of instantaneous centers, and where do they lie based on the type of motion. All right.